Hello, and welcome back again to Chapter 4 of Physics 41, University Physics 3. So let's first review what we have discussed so far in this chapter. So we have discussed about the capacitance, which is just the ratio of the charge of a capacitor over the potential difference of a capacitor. And we found out in the previous lesson that the capacitance of a parallel plate capacitor essentially doesn't depend if the capacitor is charged or not. It essentially depends on its design or its shape. Now, what will now happen if you insert something in between the plates of your capacitor? What do you think will happen to its capacitance? So for this lesson, we will explore capacitors with dielectrics. So a dielectric is essentially an insulator. So this is an example of how to make a cylindrical capacitor. So basically you just have two metal foils such as an aluminum foil, and you place uh, uh, a plastic sheet in between them and another plastic sheet after the top metal foil, so that you can roll it around without the two metal plates touching each other. Because if the two plates touch each other, then that will discharge your capacitor. So dielectrics are essentially insulators that you insert between the plates of a capacitor in order to ensure that the two plates do not touch each other. Because let's face it, it's impossible to make a capacitor with nothing between the two plates. There is always a chance that the two plates will touch each other and in the process neutralize or discharge. So the positive and negative Q charges will cancel each other out. So another purpose of a dielectric is to increase the capacitance of the capacitor of a given dimension. So that's the two main purpose of dielectric: as a separator of your metal plates, and as a multiplying factor because it increases the capacitance. By the way, in a normal face-to-face laboratory, you will actually be making a capacitor like this. You will use two aluminum foils separated with actually paper. You will use paper as your dielectric, and you make a parallel plate capacitor and a cylindrical capacitor if you want. So, but sadly, because this is now the new normal, we can't do that. So we'll just use a virtual laboratory called PhET. So a dielectric has a property called a dielectric constant. It's essentially the ratio of the capacitance when you place the dielectric and the capacitance when there is no dielectric. So that ratio is given by K. So the ratio of the new capacitance, the capacitance with dielectric, and the original capacitance without the dielectric, the capacitance in vacuum. So this value is essentially always greater than 1. If K is equal to 1, then that only means that there is no dielectric inserted. Okay. So these are just some values of dielectric constants at 20 degrees Celsius. So take note also that the capacitance now with the dielectric is just the dielectric constant times the original capacitance, the capacitance in vacuum without a dielectric. So you will notice that the dielectric, the effect of the dielectric is a multiplying factor to your original capacitance. So if your dielectric constant is 5, then it means that the new capacitance will now be 5 times the capacitance in vacuum. So in vacuum, of course, K is equal to 1 if there's nothing in between your capacitor plates. And if you have air, air is essentially rounded up to 1. So if there's only air in between your capacitor, you can just say that your K is equal to 1. So if you have Teflon, 2.1, Mylar, 3.1, PVC, 3.18, plexiglass, 3.40, glass from 5 to 10, then, oh, you will see that water actually has a large dielectric constant, 80.4, meaning if you use water as your dielectric as your dielectric between the plates of your capacitor, the capacitance will become 80.4 times than the original. But why don't we use water? Because it's hard to contain water. So that's why. So the last entry here is what we call an element called strontium titanate. And I guess this is one of the dielectrics placed in some commercial capacitors. So it's a solid. And its dielectric constant is 310, meaning the effect is 310 times the original capacitance. Okay. So let's analyze now what happens when you place a dielectric between the metal plates of your parallel plate capacitor. So here you have a parallel plate capacitor. Its initial voltage is V sub 0. And when you insert a dielectric, the voltage actually here, the voltage, you will notice the needle of the voltmeter is here, but when you insert the dielectric, it now decreases. The potential actually, or the voltage, decreases when you increase the dielectric. Take note that the capacitance is Q over the voltage. Now, if you increase the capacitance by inserting the dielectric, since this is capacitance is inversely proportional to your voltage, then that only means that the voltage will decrease. So increasing the capacitance by inserting a dielectric will actually reduce your potential difference. And we can also get the dielectric constant K as the ratio of the original voltage over the new voltage. And since the voltage is proportional to the electric field, then the ratio of the electric fields, initial and final electric fields before and after inserting the dielectric, is also equal to K. So this is what happens inside your capacitor. So this is in vacuum. The electric field is E sub 0. When you insert the dielectric, there will actually be induced charges at the two surfaces of your dielectric. So in this surface here, since this is a positive metal plate, there will be negative induced charges. And in this side, since this is a negative metal plate, there will be positive induced charges. So you can think of this as the molecules of your dielectric are realigning with the electric field. Take note that positive charges align themselves with the electric field, and negative charges align themselves opposite the direction of the electric field. So if the direction of the electric field inside your dielectric is towards the right, then that means that the positive charges will go to the right, or will align to the right, and the negative charges will be on the left. And therefore, the final electric field inside your dielectric will now be due to the difference of the surface charge in the metal plates minus the induced charge in your dielectric. So this is not the final electric field when the dielectric is now inserted. So I think you have achieved this result when you discussed about the electric field of a sheet of charge. So we can also now write the dielectric constant as a ratio of permittivities. the permittivity of the dielectric over the permittivity of free space. So the permittivity of the dielectric is essentially the dielectric constant times the permittivity of free space. Permittivity is just from the word permittivity. How a material, a dielectric, permits the flow of electric field within it. That's essentially what permittivity is. So for a parallel plate capacitor now, with the dielectric inside, so the capacitance is just K times the original capacitance in vacuum. So K times epsilon naught A over D, or since K and epsilon naught is your permittivity, so you can also write this as epsilon A over D. So that's okay. Now, everyone breaks down. There comes to a point where literally everyone breaks down. So a dielectric can also break down. So a dielectric breakdown is a phenomenon where a dielectric, which is initially an insulator, becomes a conductor. So how does that happen? So it happens when the dielectric is subjected to very strong electric fields or very high voltages. So example of that is lightning. So take note, the air is your dielectric. And during stormy weather or very bad weather, the electric fields in the atmosphere or the voltage between the sky and the ground actually becomes very, very large, such that the air breaks down. From being an insulator, it becomes a conductor. So what you see in a lightning, the lightning path that you see here are actually conducting paths from the sky towards the nearest conductor. So usually in metropolitan cities, in metro cities such as in Metro Manila, Metro Cebu, Metro Davao, in order to protect themselves from lightning, tall buildings usually have what they call lightning rods. So the lightning rods are the ones that attracts the lightning, because lightning will always travel towards the closest conductor. In the case of high-rise buildings, it's the lightning rod. So it also serves as protection for the building. So the lightning rod is connected to the ground. It's grounded, so everybody in the building is safe. So a dielectric can have a maximum electric field that it can handle before it breaks down, and that is what we call the dielectric strength. So it's just an electric field. In the case of air, the dielectric strength is 3 times 10 to the 6 Newton per Coulomb, or 3 times 10 to the 6 volt per meter. Okay. So these are some of the dielectric strengths of different materials. So you will notice here, this is increasing dielectric constant, but you will notice that there's no pattern in the dielectric strength. So it doesn't mean that if you have a higher dielectric constant, you will also have a higher or lower dielectric strength. So it has no pattern whatsoever. So let's have an example now. So let's compare a capacitor with and without a dielectric. So suppose the plates of a parallel plate capacitor have an area of 100 millimeters squared and are 5 millimeters apart. So this is actually our previous problem in the previous lesson. So the capacitor is connected to the 1.5 volt source and is then disconnected from the power supply. So a sheet of dielectric material with dielectric constant of 5 is then inserted between the plates, and the potential difference decreases while the charge remains constant. So by the way, when you insert a dielectric, even though the capacitance will change, the potential difference will change, but the charge stored within the plates of the capacitor remains the same. So letter A, compute the original capacitance. So actually we have already done this. So our result was this one, 1.77 times 10 to the negative 13 farad. So the formula that we used here is the formula C naught is equal to epsilon naught A over D. So this is the formula that we used before. Okay, so that's the answer for letter A, 1.77 times 10 to the negative 13 farad. Letter B. Find the magnitude of charge on each of the plate. So this is before inserting the dielectric. And actually, it doesn't matter. After you insert the charge, magnitude of charge will remain the same. So meaning, you can actually use, to solve for the charge, you can actually use the original capacitance and the original voltage, which is 1.5 volts. And C naught is this one, 1.77. Or you can also use the final capacitance and the final voltage. It doesn't matter which values you choose, because the charge remains the same before and after inserting the dielectric. So using that formula, so this is your capacitance, your voltage is 1.5 volts, so you just multiply this by 1.5 volts, and you will get 2.65 times 10 to the negative 13 coulombs. So that is for letter V. So let's now go to letter C. The capacitance after the dielectric is inserted. So for letter C, the new capacitance will now be the dielectric constant times the original capacitance. So if K here is 5, so this is our dielectric constant, it's 5. Therefore, it's just times 5 of this. So multiply that by 5, our result in letter A by 5, and you will get a value of, so 1.77 times 5, you get 8.85 times 10 to the negative 13, So 8.85 times 10 to the negative 13 farads. Okay, so letter D, the potential difference after the dielectric is inserted. So the dielectric constant is actually just the ratio of the original potential difference over the final potential difference. So essentially, the final potential difference is just the original divided by the dielectric constant. So this means that you divide your original potential difference by K. In this case, K is equal to 5. So 1.5 divided by 5, you will get a value of 0.3 volts. So even though the capacitance is the capacitance increased 5 folds or 5 times, the potential difference decreases by a fifth or 1/5 of the original potential difference. So for letter E, the energy stored before and after the dielectric is inserted. So what formula will you use here? So you can choose any of the three formulas, but as much as possible, use the given values. So you can use 1/2 CV squared. So you can use the formula 1/2 CV squared or Q squared over 2C or 1/2 Q times V. So for before the dielectric, so you use the original values of the capacitance and original voltage. And after, so this is your unit. And after inserting dielectric, you use the final capacitance and the final voltage or final potential difference. So you use that formula. So I will just leave that to you. This is a very simple exercise. So before inserting dielectric, the energy is 2 times 10 to the negative 13. And after inserting the dielectric, it's now 0.4. So similar to the potential difference or voltage, the potential energy also decreases by 1 over K. In this case, 1 over 5 or 1/5. That one. So increasing the capacitance essentially means decreasing the voltage, decreasing the potential energy stored by your capacitor. But the important thing is the charge remains constant. Okay. So that's the end of this lesson. So for our next lesson, we will now introduce the concept of an electrical circuit. So we will now try to connect our capacitors in basic circuit connections, the series and the parallel connections. So I will see you again next lesson.